All right, so we also, I used for this tutorial a couple of things we had learned in the Python tutorials, like interactive widgets or for example, SciPy. So again, you can check those tutorials for more info. So here we're importing the typical, scientist tools. Here we're importing CAMB. You can see where it's installed inside the Docker. Here we're importing CLASS. And here we're importing some other things. I'm using also SymPy, which is a symbolic Python package. And there's also a new thing called EinsteinPy, which I will use just to show that you can do general relativity inside Python relativity. These codes that I mentioned, CLASS and CAMB, are Einstein-Boltzmann codes. And the Einstein part of the Einstein-Boltzmann code means that you're solving equations in a space-time, so in time and three-dimensional space, following Einstein field equations of general relativity. And the Boltzmann part, which probably we will see next week for those who are more interested in details of cosmology, is just basically solving thermodynamics, fluid equations, interaction between particles, velocities, densities. Okay, so for the Einstein part, basically the main equation is the Einstein field equations of general relativity. This is, of course, an entire lecture, but what you have to know is that on the left side, you have geometry. So G, big G is a complicated function of the metric. The metric basically gives you the distances in your manifold, so it defines a manifold. And on the right-hand side, you have energy and momentum. So you put there all your matter, particles, and everything. Okay, so you notice that indices, mu and nu, they go from 0 to 3, because we have 4 dimensions, time and space. And you can, of course, solve for specific components, okay? So we will see below that the component 0, 0 is one of the most important components because it solves for the time evolution of these quantities, okay? Fine, and let's see how you can solve this equation quickly in EinsteinPy in less than 5 minutes. So first of all, you define the symbols G00, T00, and rho, which I will use later. With EinsteinPy, then you write down your Einstein field equation. So G00 equal 8 pi G T00. I'm ignoring now the cosmological constant. We will see later how the cosmological constant enters in the equations. Okay. Then we need one more constraint, which is I'm saying that the T00, so this energy momentum tensor, basically is just the density of a fluid, a perfect fluid. Okay. Then I define other symbols like my space and time. So T is time, X, Y, Z is space. And I define the scale factor, which is basically a function of time that tells you how the universe expands in all dimensions, okay? So it's a function that scales the dimensions, space dimensions of the universe. So in general relativity and what we call lambda CDM, the metric we use is this one here, which is very, very simple. It's called Friedman, Lemaitre, and Walker. It's isotropic, homogeneous. And if you write this in SymPy, you can express it as a tensor. So basically -1 in the time and a squared in the space. And then with one single function, Einstein tensor, you can compute this complicated quantity here, which I didn't write the equations for, but basically contains many derivatives of the metric and combinations of indices and contractions. So if you press this button, you will see the Einstein tensor, which is diagonal because the metric is diagonal and it's very symmetric. And now let's simplify this thing. So let's define a function that is called Hubble. Hubble function will be simply the time derivative of the scale factor. So how the velocity of space-time changes, of the space, expansion, divided by the scale factors. It's a relative velocity. And if I write an equation for that, so basically I can write h equal A dot over A. And I can substitute that equation into the Einstein tensor. And you will see that the first component, 0, 0, which I'm extracting here with these indices, it's the Hubble function squared times 3. It's very simple. If I now substitute the other quantity, which I had before, the Einstein equation reduces to 3h squared equal 8 pi g rho. Okay, so basically, the famous Hubble function equation can be extracted from general relativity directly for a very simple case, very symmetric. One next thing you can do is that you can define critical density. Is just a definition. Basically, you put everything on the left side, you leave rho alone. And if the universe contains that energy density, then the universe will be flat. Okay. And then if you divide all the densities on the right-hand side by that, you can define what we call the omegas. So basically the omegas are the densities of the species of matter, so dark matter, baryons, radiation, divided by the critical density. And these omegas in a flat space, because in a flat space, the critical density is equal to the total density, these omegas altogether summed will be equal to 1, okay? At redshift 0, so at time today. So if you see this equation here, the sum over all the omegas, so I'm actually missing here probably a factor, but basically the sum over all omegas has to be 1. And of course, h, the Hubble function today, h naught, is equal to itself today, right? So this will be a basic inequality today, okay? Is it clear until here? For those who have not seen GR before, I guess for those who have seen Cosmo before, it is pretty much standard. So one last thing that we can define is the scale factor as a function of redshift. The scale factor is, again, the thing that enters in the metric, gives you the expansion of the universe. And it's related to the redshift, so the shift in the wavelengths of the light we see from galaxies by simply this equation. It has to do with the fact that the universe expands and the radiation expands with a certain power law. Okay? So what is the universe composed of? Well, we have, thanks to experiments in Cosmo, like Planck, we have what is called precision cosmology. So we can do much more than just this GR thing. We can do really studies on how many elements we have, which particles we have, what are their properties. Here in the audience, I mean in the group, we have Valeria and Jean-Luc, which are experts in Planck, and others. So I think you might have seen this before. So you see that basically the universe is composed of 68% of dark energy, 26% of dark matter, and the rest is ordinary matter, which we call baryons. So if I put this cosmic pi into this equation above, and I know that matter decays like 8 to the minus 3 and radiation like 8 to the minus 4, and now I add the cosmological constant by hand, you will see why, I can define this function. So basically, the reason we have for adding the cosmological constant, and we will see an example, is that the sum, if you try to find out what the universe is composed of by looking at the Hubble function, you will notice that something is missing. You will notice that there is an energy density missing, and this thing is what we call the dark energy, and we express it with a cosmological constant. But yeah, of course, the idea of many people here in the group of when we study modified gravity is to see if this is more than a constant, right? But that would be for another tutorial in the far future. Okay, so one more parameter, as I mentioned before, h naught is the Hubble parameter today. It represents the rate of expansion today. It's measured in kilometers per second per megaparsec. And we have seen a couple of journal clubs about this. It's a hot topic now because, okay, Planck says that it's something around 67, and local measurement says that it's around 72. So if you take 70, what it means is that a galaxy at a distance of 1 megaparsec recedes away from us at 70 kilometers per second. Okay, so every megaparsec you're away, well, it doesn't really exactly work like that, but like basically that's the rate of acceleration of the universe. Okay, so if you go to the Planck cosmological parameters, table 1, first column, you can find the specific values of these quantities. So for this tutorial, we will only focus on background, which is omega c, dark matter, omega b, omega radiation, and omega lambda. So Planck shows you omega b times h squared. Little h is simply h naught here above divided by 100. Okay. So these are the parameters that are shown in the table, and you can compare, sorry, you can compute some derived parameters, which is more the ones we would use, which are basically the energy fraction of total matter. So I have to take omega m h squared and divide it by h squared, right? So I get the big omega. So small omega is what we call when you multiply big omega times h squared, okay? And so in this way, I can get a dictionary of parameters, which I can evaluate for whatever parameter. And I'm using dictionaries here because also CAMB and CLASS use dictionaries for this kind of stuff. So it's useful to do it. One parameter I'm taking out of my own notes is radiation, which is more difficult to obtain because it depends on the CMB temperature, relativistic species, and so on and so forth. So it's anyway very, very small today, so it can be neglected in this equation, but this is more or less the parameter I obtain. Okay, so as I was saying before, omega lambda is simply what is left when you find that the universe doesn't have the critical density. So you find that the universe is flat for many reasons, and spatially flat, and then you sum up the energy densities and you find it's not one. So whatever is left, it's omega lambda. So actually both codes, CAMB and CLASS, work like that. You usually don't specify omega lambda. You specify omega c, omega b, whatever, and what is left is what the code takes as omega lambda. Even curvature, I think, for example, in CAMB has more priority. You define first, if you want curvature, which I'm not talking about this tutorial, that will also reduce the amount of omega lambda you have. So we get here 68% of lambda, which is roughly what we have here. Okay, so maybe this plot is not up to date with Planck 2018. Okay, so let's code our own Hubble function. Until here, everything fine? If I'm losing someone in the Cosmo, let me know. But I think that was basically the theoretical part, and now we will just see how different codes work. So I'm defining here A of z. Then I'm defining this constraint. So omega lambda is 1 minus everything else. And then I'm defining another function, which is basically a function that extracts from this dictionary the cosmological parameters. So it extracts the parameters. If it doesn't find them in the dictionary, it will just take Planck 18 as default with this function get. And it will also return omega lambda and returns basically a tuple of parameters. So if I run this cosmological parameters function with 0 arguments, I get the cosmological parameters. If I want to change, for example, h naught, I just pass a dictionary with h naught. And you will see that the only one that changed is 67 to 72. And finally, I code this Hubble function. I'm just coding this because I want to show you that this is actually very easy. I mean, this is very easy to do, and the results you get will be basically identical to what CAMB and CLASS gets. So there is nothing magical in CAMB and CLASS in the background, kind of, let's say, unless you go to very high redshifts. So again, the Hubble function at 0 should give me h naught. If I pass another dictionary, the one I define here, of course, I will get the value of that h naught. And if I want to create a crazy cosmology, of course, I can do it, and I can pass it to these functions. So let's see how this crazy cosmology looks like. So you see that this is the Hubble function. I'm showing here in log space in Z. The first one is Planck in orange. The local is with h naught equals 72. So this tiny difference here that you don't see almost in the plot is what cosmologists are fighting about. And the green one is a crazy cosmology, which we know this is ruled out by many, many reasons. Okay, both also because of omega c is very, very big, mostly because of that. So I have a theoretical question for you. So you see that for redshift almost 0, the Hubble constant is a function. Sorry, the Hubble function is a constant. And if this is the velocity, a dot over a, what does it mean for the expansion of the universe? What kind of function describes the expansion a? Of course, not else. This is a question for people that are not doing cosmology every day, of course. But does anyone have an answer? I mean, you can solve this. It's a very tiny differential equation. So a dot over a equal a constant. It's very simple. You just take, I will kind of write here what happens. So basically, you have dA dt divided by a. This is the same as d ln a dt. And this is a constant. So you can write it as d ln a equal constant times dt. And then you integrate on both sides and take the exponential, and then you get e equal exponential of ct. So the reason that the Hubble function is basically a constant today, or the consequence is that the universe is expanding with an accelerated exponential expansion. So in the far future, when omega lambda will dominate the universe, it will be exactly an exponential expansion. Okay, cool. So now let's look into CAMB and CLASS. Okay, so CAMB is basically a code that has been developed for many years by Anthony Lewis and collaborators. He's in the UK. It has been used for the data analysis of Planck. So Valeria, for example, is a very knows this very well because she has been working with data analysis. She has been running CAMB, CosmoMC, and all these kind of things. And for many years, it was only written in Fortran. So even when I did my master's and PhD, so that's when I had to code my own wrapper for Mathematica. And like the Python wrapper really did not work at all until very recently. And it's very simple to use. I mean, you can click here on these things to see more details about it. There's a good documentation. So I think they have done a good job that people in CosmoStat could be proud of, like documentation and stuff like that. And you will see that CLASS is not so much like that. I mean, it's different. Like CLASS has a lot more learning material, but it doesn't have such a good documentation. So first of all, what you do is you call these CAMB params. You can call it with an empty, well, no arguments. Then these parameters, it's an object, and you can set a cosmology. So here I'm setting h naught to our dictionary above, h naught, omega b h squared to omega b h squared, and omega c h squared. So in this way, I'm defining the cosmology. If you follow the next tutorial, you will see that there's a lot of other stuff for perturbations that you can set. But for background, this is basically it. There are a couple of extra things, but this is basically it. So you see that if now parse has an attribute h naught, and it corresponds to the h naught I passed, of course. If you want to get now background quantities, you just call get results, and then you call calc background. This, you see that it took like a second, and it's because it's calculating all these background quantities, but it's also doing other stuff in the background. So, for example, it calculated the age of the universe. It calculated things related to recombination, so to the time of the CMB. It calculated also, for example, when was the equality between matter and radiation, and so on. And now, if you remember the dictionary we had, we had the age of the universe from the Planck paper. We can compare what we get here by not doing much, right? Like, as I said, this is for this tutorial, everything, but if you want to be precise, there's other stuff like, reionization parameters and other things. So only with this very rough setting, we can get an age of the universe, which is only 0.3 million years different than the one calculated by Planck. So this difference here is basically everything else that comes from the early universe that modifies these equations. Okay, so exercise 1, which you can do at home, is what will be the age of the universe in our crazy cosmology. So just take this dictionary, pass it to CAMB. Be careful that you have to convert to the right parameters and calculate the crazy cosmology. I got 11 giga-years, which means 2 giga-years difference from Planck. Okay, so now the Hubble function is simply evaluated by running results.hubble parameter. A good thing about CAMB and CLASS is that when you have these objects, so you can do, oh, it's a bit slow. You can do results dot and then tab, and you can see all the stuff that you can actually call. Okay, so you have other things that we will not cover, like growth factors, growth rate, and other things will not work because we have not specified anything for perturbation. So actually only the background things will work. So things like power spectra have to be defined before actually calling them. So let's compare our homemade HF set versus CAMB. It's basically the same, exactly the same. You see that if I plot in linear space, you don't see how flat H is today. So actually this flatness of H is very recent in redshift. It's only very recent. That's called could be called the coincidence problem, right? Like this thing of lambda taking over the universe only happens very, very recently. Okay, so let's do the same thing in CLASS. CLASS is a bit more modern, I would say. It's written by Julien Lesgouche, who was in Geneva, France, and then now in Germany. It's in C language because they claim it's much faster. And it has been used for data analysis of galaxy surveys, for example. You can see here in this link hours of courses and learning material. There are tutorials, videos, and everything. So this is our dictionary from before. Let's create another dictionary for CLASS. I'm just passing H0, omega B, and omega C. Look that CLASS is more flexible. If you look at CAMB, you actually have to pass small omegas. So these small omegas are big omegas times H squared, and you only can pass these two. CLASS understands everything. So you can pass a small omega, a big omega. You can, for example, not pass H0, but then pass other things that will derive H0. So CLASS tries to interpret what you pass, and whatever is not passed, it takes default. CAMB is not like that. So you take the dictionary, you create an empty cosmology, you set the parameters, and then you compute. You see that this computation, which in my opinion, much faster, and also I think it's claimed by CLASS, much faster than CAMB. So the background is computed in milliseconds because it's really just doing the background. It's not doing anything else. You will have an attribute for the Hubble function. You will see current list of derived parameters. You will see in the documentation that I put here, you can see which kind of dictionary keys you can access. Unfortunately, I didn't find a way of accessing all the keys. So it seems this object doesn't have like a dictionary where you can see all these keys. So, but if someone knows, yeah, let me know. You can also, for example, find the age. And here you will see that the age we get of the universe compared to the Planck age is 17 million years, which means there are some parameters hidden here that are not the ones from Planck, and the difference is already much bigger. Okay, and here you see other available parameters like omega 0 fluid, in case you specify a dark energy fluid, omega lambda, conformal age, other things like neutrino mass, and so on. For the background, and we will see later, it also calculates distances. Distances are very important in cosmology. So you can see the keys. This one does have keys, not like this one. And it shows you all the things you can compute. For example, the densities themselves, you can compute them. And you can compute the pressure of certain species and so on. Okay, so one more thing is that also CLASS shows you which set it used for calculating the background. And if you put here shape, you see that it's 4,000 set points. So it's quite a lot. So if you call this background function in units of 1 over megaparsec, it will give you an array of 4,620. But it's more useful actually to have an interpolating function, and also CLASS provides this. So one thing that you have to do in CLASS is that CLASS, if you look at it, shows everything in megaparsec units. So if you want to convert to kilometers per second per megaparsec, you have to multiply 1 over megaparsec times kilometers per second, because these units are basically with c, the speed of light, set equal to 1. So you can get the speed of light from SciPy, and you can then multiply this array by speed of light, and you will get 67.32. Is this clear with the units? I mean, it's I think at the beginning not very straightforward, but basically what is happening is that in these units, kilometer per second per megaparsec, since you're setting c equal to 1, the kilometers per second disappear, and that's why you get 1 over megaparsec. So to recover kilometers per second per megaparsec, you need to multiply with the speed of light. Okay, so now instead of an array like this one, you can also get interpolating functions like Hubble, and you can evaluate them at any redshift. And what I find a bit annoying within CAMB and CLASS is that it's not unified in how arguments are and all these things. So for example, for CLASS, I can only evaluate scalars. If I pass here a list, it will return an error. While if you look at CAMB, actually here, you see that this results Hubble parameter, I can evaluate directly an array. So it's a bit annoying if you want to work with both codes, but I think it doesn't really happen that much, that you work with both codes at the same time. I think you can choose the code you like the most, and they are basically doing the same. There is even a paper on comparing these two codes for Lambda CDM. So if I define this H class, which is an array computed with class of the Hubble function, another one computed with CAMB, and I divide it by the manual Hubble function that I had coded myself, you see that the difference is, of course, well, it's sub percent level. There is some weird stuff happening here, probably because of the sampling in the redshift array. So if I increase the sampling, it probably changes and it's a bit smoother, you see. And the funny thing is that the Hubble function from CLASS seems to agree perfectly with the one I coded. So somehow it has nothing else. Well, the one from CAMB seems it has something else that is happening at these redshifts. If I go, of course, to higher redshifts, you expect to see huge differences, of course, because I'm not taking into account neutrinos and all that stuff. So yeah, so it's actually, that's it. That's basically the function that you want to compute. And also class provides a way of cleaning the structures. So you can clean the, if you're looping over many cosmologies, it seems that your memory will run out. So you can clean up this memory by running this, okay? Okay, so now a bit more of cosmology. So let's define distances. So distances are very useful because you can, for example, find the distance to supernovae, find the distances, perpendicular distances like the BAO scale and all this kind of stuff. So in one dimension, it's very, so one spatial dimension, I can show it here in a couple of steps. So the line element that we had before, which is basically, sorry for moving so fast, which basically defines the metric. Notice that the time has a negative so a negative sign in front. So this line element, because of how general relativity works, defines geodesics. Okay, and if you set this line element to 0, you are defining light. So light moves in null geodesics. So if you set this line element to 0, you can solve for dx. So dx is simply c dt divided by a of t. T is cosmic time, so time that basically is sliced for all the observers in the universe. And then you can integrate this dx and find this distance, which we call comoving distance, by integrating the right-hand side. Here in cosmic time, if I do a change of variable, which is simply a chain rule, I get dA over a squared times h. And if I change to redshift, it's even simpler. It's just t set over h offset. So this is how you define the comoving distance. This is basically the distance between you here and some galaxy, let's say a redshift set. And the way we communicate with that galaxy is with light. So there is nothing faster than light. So this is basically also the speed of propagation of information. Okay, so, and another distance that you can define apart from the comoving one is the angular diameter distance. I will not show the definition or how you define it, but basically after very, very little algebra, you see that this distance, what it basically tells you is what is the distance of an object of size L that you see with a certain angle in the sky theta. And it's just a definition that is useful because of astronomy. And this gives basically just the comoving distance divided by 1 plus set. So this one is useful in in looking at objects in the universe, for example, structures or something. Okay. So for CAMB, so is it clear here? Is this derivation? I'm so asking for the people who don't have not taken a course on cosmology or on GR. So in CAMB, you can evaluate the angular diameter distance by simply remembering that results has a lot of results, and you just evaluate angular diameter distance in this array, and also the comoving distance. In CLASS, since it doesn't accept arrays, you have to do list comprehension. So you do a list comprehension with Cosmo dot angular distance and the redshift for all the redshifts in this array. And there is a function for getting R, but this function returns R and dset the R. Dset the R is probably very useful for doing variable transformations. For example, in lensing the kernels and stuff, you can write them in terms of R or in terms of redshift. And I guess this is why this function returns also dset the R, but we don't need it. So we can just work with R set, which is basically the first element of this tuple. And that's basically extracted by just doing Cosmo dot set of R. And you see how a bit inconsistent this is, because here there is no way of passing an array, but here you can pass an array. So it would be really nice if the Python wrapper one also have here the possibility to have arrays. Now let's plot them together. So let's plot the comoving distance r and also the angular distance for CAMB and CLASS. And you see for the comoving distance, it's pretty standard, you would say. So basically the distance as a function of redshift grows and grows and grows and grows. So it just kind of has a relative like asymptote, but it keeps growing, right? While the angular diameter distance has a funny behavior. So it grows very fast at small redshifts, and then it goes down. And that's because if you have an object, imagine you have an object of 100 megaparsec, and you move it towards the Big Bang, the object at the Big Bang, it would appear to cover the entire sky, right? It would basically, the angle that this object covers would be the whole sky. So basically this angular diameter distance tells you how far this object looks in terms of angle. But usually we forget about all these definitions in cosmology, and we don't care, and we just work with it. But it has some kind of reason for being there. So this distance, as I showed you here, is an integral that you can do numerically very fast for whatever function you put here. But if you put a very simple function like h like 8 to the minus 3/2, which is what you get when matter dominates. Okay, this is theoretical question 2. So basically you go here to this function, you convert this to a, and then you look what happens if only these two terms, omega c and omega b, dominate. What will happen with this equation? And also, if matter dominates, the sum of omegas for matter will be 1, right? So basically it disappears from the equation, and you end up with something very simple like h naught to the a minus 3/2. And then again, you can do SymPy. SymPy also integrates. So it would be nice to do SymPy for many things, but I personally, well, of course, I have always used Mathematica for these kind of things, and I still feel that Mathematica is easier to handle. Also because of the prims, because of how do you define things. But anyway, SymPy seems to be very nice, and it's growing in popularity. So you can basically integrate this function h naught a to the minus 3/2 for matter domination, and then you substitute the definition of redshift. And then you have 2 divided by h naught. I just put an s to say that this is symbolic. 1 minus 1 over z plus 1 to the 1/2. So if we code this up, I'm coding it in the same way that I was coding the Hubble function. You see that I get a result. And let's compare now the angular diameter distance I get for matter domination in a very simple case to what I get from CAMB in lambda CDM. And I'm using here XKCD plot, which is very easy to use from Matplotlib. So this is why I tell you that cosmologists find out that there is lambda, right? That there is a cosmological constant, because basically you can put data on this plot, for example, from supernovae, and you find that the data will lie on the green line. And if you had only matter in the universe, it would lie in the red line. So it's very easy to, in a simple way, to rule out that there is no accelerated expansion. So what is the accelerated expansion? We still don't know, but it's very easy to find that there must be something else than matter. And it seems to be right now dominating. So you see how big the difference is. And also you can see something from this plot, which is that at redshift 3 and above redshift 3, so for early time, so very far in the past, this difference was very small. So this also tells you when dark energy started dominating. So from redshift 3 to now. And then of course today distance is 0, right? So of course it will converge here, but it tells you that basically at redshift 1 is where this difference is bigger. So maybe it's also good that we're focusing our experiments in redshift 1, right? Where we know that, for example, this quantity is big. This is a quantity that can be measured with Euclid, with BAO. It will be measured with DESI. Has been measured by Boss. Many other experiments, and even might be that one day we have also baryon acoustic oscillations in weak lensing, and you can measure this DA. And now let me show you an interactive plot. I had explained these interactive plots in the tutorial I gave last year, but basically the only thing I need is to define a plot function and pass it to interact, which is a function from IPy widgets. So first I define an interactive class angular diameter distance. I'm using class because it's faster than CAMB. So it passes a dictionary. I create a cosmology, empty cosmology. I pass the dictionary parameters to the cosmology. I compute the background, and then I extract the angular diameter distance for all the redshifts. So you see that if I pass 100 redshifts, I will get an array of 100. And then this is the plot function. So you will see that what I'm doing here is defining this dictionary. I'm just passing two variables because these are the ones I want to control with the interactive plot. I pass the dictionary to DA. I pass the dictionary to my function I defined here, the symbolic one, and then I plot them. And is this working for everyone in their notebooks? Because I didn't check if this was kind of installed. I just suppose that it's in IPython.
It's working fine for me.
Okay, thanks. So you can see that again, here you will see that changing H0 doesn't improve the agreement, right? We don't solve the dark energy problem by just changing H0. H0 only changes the y-axis. So it just changes how far objects are, right? But if I change omega c, the cold dark matter, it solves basically, or kind of would explain the agreement. So in order to have a matter dominated universe, I would need an omega cold dark matter of 0.95. Everything below that, you will start to see a discrepancy. And actually omega cold dark matter is rather 0.2. So, 0.25. So you see that there's a huge difference, as we saw before. It's very easy to do these interactive plots. You just define a plotting function and you pass two parameters. You can do more parameters, but I guess it would start getting a bit slow. But yeah, it's very nice. Then, as a final step of the tutorial, I wanted to show you some, let's say, real data. This is not, very, this is not a tutorial on how to do data analysis. Hopefully we have something like that, like, parameter estimation. But I'm taking data that we compiled in this paper that I did with my former master thesis supervisor in Heidelberg. And it's just data that we found in different papers from H of Z divided by H0. So it's just what people also call big E of Z. So it's just compiled from baryon acoustic oscillations, cosmic chronometers, and supernovae. Cosmic chronometers is like trying to get H of Z from the ages of galaxies and stuff like that. So it's in materials. You can see the data here. It has 33 entries and 3 columns. the first column is redshift, the second column is h divided by h naught, and the third column is the error bars. Then let me define another cosmology dictionary. And let's plot this data versus this new cosmology that I just made up here by hand with local h0 measurements and a bit more CDM. And also compared to the one that I had from Planck. And you see that the data in h, sorry, actually the y label should be h divided by h0. The data is quite bad still, because this is very high redshifts. I'm focusing here on redshifts bigger than 1. Here you only have few points coming from BAO stuff and these other cosmic chronometers, but you know, supernovae. I mean, you guys probably in the audience know much more about some of these data sets than me, but basically this is roughly the status right now. So you can see that you can do a lot of crazy cosmologies with this data because the error bars are huge. And finally, you can also integrate this data without the error bars, of course, and try to get the angular diameter distance from this data. So what I'm doing here is computing the integrand of this equation. So this integral, going up again, this one, from the data. So I just basically take the data, split it into x, y, and the error bars. I take the cosmological parameters because I need h0 to multiply. This data is h over h0, so I need h0 to multiply it and get the correct units. And then I do an integration with Simpson of an array. That's the cool thing about this Simpson integration. You can just integrate an array, and then I can compute the comoving distance and the angular distance of these data points. You see the data points are in these redshifts. This is the comoving distance of the data points at redshift 0.5. By the way, this is already returning a kind of an interpolating function, right? Because the integral returns, I can evaluate it wherever I want, basically. And finally, I can also plot the distance compared to Planck and compared to a matter-dominated universe. So you see, this green one has a very low h0 value. So if I start increasing the h0 value, it doesn't really agree that well. That's because omega c is very big. So actually I have to put omega c to what we know is more or less okay. And then I can play a bit with the h0. You can change here, for example, the range of the plot and how many steps. So if I put now, again, this in 0.25, you can see that the agreement, I mean, this is of course not real data analysis, right? But you can see that the agreement is a bit better with a bit of a higher h0 than if I go to something like 65, especially at higher redshifts. So you can see that this is roughly, since these are measurements of things that are not primordial, are local, kind of like supernovae or BAO things, you can see that there is something there with this h0 tension. Of course, this is not how people actually do it by far. I'm ignoring many things here, but it's just for you to play around. So the exercise 2 is find the values that best match the angular diameter distance data. And so yeah, this is the end of the tutorial. Actually,